It refused food for 5 years, and when it died, it was not thin. Specimen number 1 arrived at Toba Aquarium in Mie Prefecture, Japan in September 2007, a giant isopod, species Bathynomus giganteus. The size of a rugby ball, armored in grey plates, compound eyes like 2 dark stones set in ancient bone. Staff fed it regularly. It ate. Then, in January 2009, it stopped. Not briefly, not for a week, not for a season. 5 years, 43 days, every feeding attempt logged, every refusal marked with a dash in the aquarium's records. Keeper Tomoyuki Miura and his team offered fish, squid, shellfish. The animal sat motionless on the substrate, mandibles sealed, legs folded. The food was removed, the log was updated. The next attempt was scheduled. This went on until the 14th of February 2014. When specimen number 1 finally died, Miura's team did not find a wasted body, no visible muscle loss, no collapse of internal structure. We were astounded that it had survived for so long without eating. Miura stated in the aquarium's formal release that month, the digestive tract was empty, clean, as though the animal had simply decided to stop processing the world. Here is what makes this stranger than it sounds. Bathynomus giganteus is not a distant deep-sea alien. It is more closely related to the pillbug in your garden than to any crab or lobster. Extreme gigantism. Terrestrial origins. Pushed into the abyss over millions of years, and somewhere in that descent, it learned something about time that nothing else has. The real question was never how long it lasted. The question was what was happening inside that body, biologically, chemically, at the cellular level. A post-mortem analysis began immediately. What the research team found required them to build equipment that did not yet exist. That equipment produced a single number. By the end of this video, that number will change what you think the word survival actually means. NASA-affiliated engineers have already requested the tissue data. The obvious answer was hibernation. Every biologist reached for it first. Bears do it. Lungfish do it. When resources disappear, warm-blooded and cold-blooded animals alike can dial down their metabolism to a crawl, burning almost nothing, waiting for conditions to improve. The scientific term is torpor. It is well documented, well understood, and it seemed to fit specimen No. 1 perfectly. So, in February 2014, after the animal died, the researchers at Toba Aquarium and Kagoshima University ran the standard checks. If torpor had sustained this isopod through 5 years and 43 days without food, the evidence should have been there in the tissue. It wasn't. Shinta Fujimoto's team at Kagoshima University looked for the hormonal signatures that torpor leaves behind. In hibernating mammals, in estivating lungfish, those markers are unmistakable. The body announces what it is doing. Specimen No. 1 showed none of them. The hemolymph, the pale copper-tinged fluid that moves through a crustacean's body, the way blood moves through yours, showed no torpor chemistry whatsoever. Then came the temperature data. Torpor typically involves a drop in core body temperature relative to the environment, but this was a deep-sea animal in a controlled tank. The temperature probes showed something flat and strange. The isopod's tissue temperature matched the surrounding water exactly. No gradient, no thermal signature of a suppressed system running below ambient. The oxygen levels were ruled out too. Low oxygen environments can force metabolic slowdown in some species. The tank was not hypoxic. The torpor framework collapsed. Here is what that left the researchers with: an animal that had not hibernated, had not estivated, had not entered any recognized state of suspended metabolism. And it had still survived 5 years without a single calorie. If it wasn't torpor running that body, then...
Here is what the researchers expected to find. A body that had consumed itself. Muscle tissue degraded. Reserves stripped. The slow, visible evidence of a creature that had burned through everything it had, over 5 years, until nothing was left. That is not what they found. The post-mortem examination in February 2014 showed tissue that was structured, intact, the exoskeleton fully formed, the digestive tract empty, yes, but the surrounding biology looked nothing like an animal that had starved. It looked like an animal that had simply stopped. Shinta Fujimoto's team at Kagoshima University ran the metabolic measurements. Standard respirometry equipment, the kind used across marine biology labs worldwide, registered almost nothing. The oxygen consumption was so low the instruments could barely resolve it. So the team did something unusual. They built a custom sealed chamber system, engineered specifically to detect consumption below levels any existing equipment could reliably measure. The readings they got back changed the question entirely. This was not hibernation, not the slow burn of a bear in January, drawing down fat reserves across a cold season. What the tissue analysis pointed toward was cellular respiration throttled at the mitochondrial level, the biological equivalent of switching off the engine rather than idling it, closer to suspended animation than starvation. A process that, as Fujimoto's team noted in their published findings, no synthetic system has yet replicated. The isopod was not in the deep sea when it did this. It was in a warm, oxygenated, pressurized-to-surface aquarium tank in my prefecture. Temperature normal. Salinity normal. Oxygen normal. The data logs across 5 years showed not a single environmental trigger. Nothing external initiated the shutdown. Something inside the animal did. The mechanism is not a response to the deep sea. It is something the animal carries with it, something internal, autonomous, and still unidentified. The environment did not flip the switch.
Here is the number, the one this entire video was building toward. After specimen number 1 died at Toba Aquarium on the 14th of February 2014, Shinta Fujimoto's team at Kagoshima University began measuring what was left, not weight, not tissue mass, metabolic rate. How much oxygen had this animal actually been consuming during those 5 years and 43 days? Their standard respirometry equipment registered nothing. Flatline. They assumed instrument failure. They were wrong. The team engineered a custom sealed chamber system capable of detecting oxygen consumption below 0.01 milliliters per hour. That is not a rounding error. That is a purpose-built scientific instrument designed around a single animal's impossibly quiet body. The rate they recorded was 50 times slower than any previously measured marine crustacean of comparable body mass. Fujimoto's team confirmed it, then confirmed it again. The research team's own published statement described equipment that could barely detect what the isopod was doing. The isopod had not been slowly starving. It had pharmacologically suspended its own metabolism, autonomously. In a stable, oxygenated, pressureless tank, no external trigger, no crisis, the shutdown came from inside. That is the thing nobody had seen before. The mechanism was endogenous, written into the biology itself. Remember the empty tank from the beginning of this video, the animal that refused food for 5 years and died intact, undiminished. The question was never whether it could survive, the question was how. Now there is an answer, and the answer is a number so small it broke the instruments. NASA's Ames Research Center and JAXA have both formally requested the tissue dataset, not out of curiosity, for long-duration spaceflight metabolism research. The distance between Earth and Mars is 7 months of human metabolic demand. The isopods solved a version of that problem before humans had a space program. One animal, one tank in Mi Prefecture, one number that forced scientists to build new tools just to read it. Subscribe for a new breakdown like this every day.